A decade ago, talking about engineered human tissues and swapping them with natural ones looked like a science fiction movie for most of the people, while to tissue engineers this was a real goal and challenge, which encouraged them to hardly work in the laboratory. Tissue engineering evolved from the field of biomaterials development and refers to the practice of combining scaffolds, cells, and biologically active molecules into functional tissues. The ultimate goal of tissue engineering is to assemble functional constructs that restore, maintain, or improve damaged tissues or whole organs. Population aging and its related problems greatly attracted tissue engineers' attention and made them to speed up the projects that can improve the quality of life of elderly. Among different human tissues, the poor self-regeneration of the cartilage, especially articular cartilage, is becoming a great concern to the elderly or athletic populations. Articular cartilage is the highly specialized connective tissue of joints, and its principal function is to provide a smooth, lubricated surface for articulation and to facilitate the transmission of loads with low frictional coefficient. The interesting thing is that unlike other tissues, articular cartilage is devoid of blood vessels and nerves, which resulted in limited capacity for intrinsic healing and repair. Therefore, there is a need to develop a non-invasive treatment to replace a damaged cartilage with a custom-made one. But fabricating a tissue mimetic structure is not as easy as what we think. First of all, we need to have a suitable method for fabricating a tissue-engineered structure. Thanks to the nanotechnology advances, nowadays 3D printing provides researchers with this opportunity to create most accurate 3D tissue models by using CT and MRI scans. However, developing a suitable ink with similar mechanical features to the human cartilage still is considered as a main challenge of articular cartilage 3D printing. Among different materials that have been used in fabricating tissues, silicone has attracted a great interest due to its remarkable features such as flexibility and biocompatibility. However, some drawbacks such as slow curing speed, low viscosity, and hydrophobicity of the existing ones are challenges that hinder silicone application in 3D printing. My research aims to develop a uv-curable and hydrophilic silicone-based bioink consisting of aminosilicone, methacrylate, and cellulose nanocrystal to fabricate the articular cartilage. Aminosilicone is not only hydrophilic but is versatile due to the presence of active sites that can interact with various curing agents which are necessary for rapidly curing 3D printed tissue models. Just consider that you can print a structure and cross-link it in less than a second without any use of molding or any prolonged curing methods. For this purpose, methacrylate, a non-UV curing agent, can be introduced to the surface of the aminosilicone to instantly cure the ink as it is extruded from the 3D printer nozzle by using UV light exposure. For this purpose, methacrylate, a non-UV curing agent, can be introduced to the surface of the aminosilicone to instantly cure the ink as it is extruded from the 3D printer nozzle by using UV light exposure. Besides UV curability and hydrophilicity features, the ink should possess proper mechanical properties and be able to be extruded through the nozzle and recover its shape after extrusion, which is known as shear-thinning properties. These features can be effectively tuned by adding modifier polymers such as cellulose nanocrystal. Ultimately, this research is vital for the development of a versatile ink that can be used not only to fabricate biocompatible tissue mimetic models but also for in situ surgery applications.